Our final project is audio recognition and diarization. Here is the overview of our presentation, and let's start with the introduction. Audio recognition is the technique that enables the recognition of spoken language into text, and audio diarization is the process of partitioning an input audio into homogeneous segments according to the speaker's identity. The purpose of our project is to be able to recognize and diarize the audio of the animation Kimi no Nawa. In the last few decades, speech and language technology has advanced significantly. However, machines still have difficulties understanding natural conversation with multiple speakers. Therefore, one of the first steps in understanding natural conversation is to be able to recognize the spoken word and their corresponding speakers. Currently, a lot of effort has been made for speech recognition and speech diarization, but most existing methods handle these two tasks separately. Our goal is try to combine them into one task.
Let's talk about the task of our project. Inspired by the paper End-to-End Speaker Diarization with Permutation-Free Objectives, we have three main tasks: joint speech recognition, segmentation, and diarization. To achieve these objectives, we adopt the idea from listen, attend, and spell architecture for speech recognition, and the end-to-end neural speaker diarization architecture for speaker classification. The dataset used is the audio file and the corresponding transcription file of the film Kimi no Nawa. After processing, we got 1,393 audio snippets with the corresponding speaker label for training and validation.
The model consists of two modules. One is the recognition module. It is to take the audio as the input and to generate transcriptions. The other one is the diarization module. It is a process to determine who is the speaker. The method in the recognition module mainly adapt from listen, attend, and spell. We want to model each character output as a conditional distribution over the previous characters and the input data. The listener is an acoustic model encoder to extract features. The listen operation uses a bidirectional long short-term memory RNN with a pyramid structure. In our model, we stack 3 PBLSTMs on top of the bottom BLSTM layer. A linear layer is followed to generate the key and the value we need in the decoder. The speller is an attention-based character decoder, which produces a probability distribution over character sequences. At every time step, the distribution for y is a function of the decoder state and the context. The context vector is produced by attention mechanism. The decoder state is a function of the previous decoder state, the previously emitted character, and the previous context. The diarization module is to identify who is the speaker. This is a supervised learning, and the speaker label is a vector with the length of the number of speakers. In our case, the number of speakers is 52. The most probable speaker label sequence is estimated among all possible speaker label sequences. The conditional probability of y given x can be factorized using conditional independence assumption. The frame-wise posterior is modeled with BALSTM, followed by a fully connected linear layer. Here we used two-layer BLSTM. Cross-entropy loss is used to calculate the loss. Here is the flowchart of the complete model. The two modules share the stacked BLSTM layers.
Train the model for 70 epochs and the model loss have converged. The word error rate is consistently higher than 100%, indicating that the predictions are far from accurate. For the diarization model, we trained it for 90 epochs to achieve the best result, accuracy of 56%. We have 52 speakers in total for the diarization task, and many of those speakers have only one or two utterances. It is difficult to train the model to predict the utterances made by the various speakers. We tried training with various batch sizes, optimizers, learning rate schedulers, but none made significant differences. Our potential issue is that the training data size is way too small. Our total dataset contains 1,393 transcriptions, and among them only 1,372 utterances are valid speech. The total speech duration is less than 1.5 hours. Compared to other popular speech datasets, such as libre speech datasets, the total speech duration of which amounts to 960 hours. Our dataset contains too little labeled training data. The small size of data poses difficulty to train an effective LAS model. Additionally, the model we proposed achieved reasonable performance on larger datasets such as Wall Street Journal 1, which contains 78,000 training utterances and 73 hours of labeled speech data. The relative success of the same model architecture on bigger dataset made us believe that the dataset size for the project is the main obstacle to successful training. One solution we propose and a further study is to pre-train a self-supervised model on larger corpus of unlabeled data and fine-tune with a limited size of labeled data to achieve a better result.
Finally, conclusion. From the results, we can observe that the LAS architecture presents limited ability to translate the 1,372 valid audio snippets into proper sentences. Regarding the diarization module, the performance is not bad, which is able to achieve an accuracy of 56% in predicting the speaker. We suspect that the relatively small and biased dataset might be the cause of the bad performance of the LAS model. Therefore, in the future, we will try to first pre-train the whole model with a larger dataset to see how it works. If larger dataset is not available, self-supervised learning is a good alternative. Finally, we will further tune the threshold in the diarization process to improve its performance. Thank you for watching.